Previously, we have seen that the coordinate ring of an affine algebraic set could fail to be catenary if the affine algebraic set is reducible. It turns out that this is the only obstruction. So coordinate rings of irreducible affine algebraic sets are gonna be catenary. In other words, finitely generated K-algebra that are integral domain must be catenary. Since every such algebra is just a quotient of the polynomial ring by some prime ideal, and catenary is inheritable by quotient, it suffices for us to show that the polynomial ring is catenary. So let us prove that the polynomial ring in n variable is catenary by induction on the number of variables. Actually, we'll show a bit more than that. We'll not only show that all the maximal chain of prime ideals have the same length, we'll actually also show that dot length must be equal to n. Alright, so let us start with the base case when n is equal to 1. Now recall that the degree map on polynomials give a Euclidean norm on the polynomial ring with one variable, and thus the polynomial ring with one variable is a Euclidean domain and hence a PID. Now next, recall that in a PID, all non-zero prime ideals must be maximal because every non-zero prime ideal is gonna be generated by a single irreducible polynomial, and such an ideal must be maximal. Thus, every maximal chain of prime ideal must be of this form, because no two non-zero prime ideals can contain each other since they are all maximal. Note that 0 is a prime ideal because this is an integral domain. So we see that indeed all chains of prime ideal, all maximal chain of prime ideals have the same length, and that length is equal to 1, the number of variables. Alright, so now let us suppose that the polynomial ring in n-1 variable is catenary, and all maximal chain of prime ideals in that polynomial ring is gonna have length n-1. And we want to show that all maximal chain in the polynomial ring in n variable are gonna have length n. So let's take one such maximal chain. Note that again it's gonna start with 0 because this polynomial ring is a domain. Now we want to use the induction hypothesis somehow, and at first it's very tempting to do the following. At first it's very tempting to just intersect every ideal in this chain with the polynomial ring in n-1 variable. But we can't apply the induction hypothesis here because this is not necessarily gonna be a maximal chain, because the primes in this chain might no longer be distinct, and in fact they generally will not be. Otherwise this polynomial ring would have a maximal chain of length n. For example, if we intersect this chain of prime ideals of the polynomial ring in n variable down to this ring, then these two ideals are gonna coincide, which makes sense because we should not be able to get a chain of length n inside the polynomial ring with n-1 variables. So to be able to effectively use the induction hypothesis by contracting the prime ideals down, we need to ask, in which situations do distinct prime ideals contract down, intersect down to distinct prime ideals? This is answered by the following incomparability property from commutative algebra. This lemma says that if B over A is an integral extension of rings, where here we view A as a subring of B, and P, Q are two prime ideals of B that contract down to the same ideal in A, then they must be the same ideal in B to begin with. Equivalently, distinct prime ideals in B contract down to distinct prime ideals of A. We'll prove this in the next video. For now, let us come back to the proof of the catenariness, I guess, of the polynomial rings in n variable. To use the induction hypothesis, we somehow want to contract the prime ideals down, right, to polynomial rings in n-1 variable. The trouble is, to be able to use this incomparability property, we need an integral extension, whereas this extension is not integral, as xn is algebraically independent from x1 to xn-1 and thus cannot satisfy a monic polynomial with coefficient in x1 to xn-1. However, observe that if we quotient this polynomial ring out by some polynomial in the xi such that the leading coefficient of xn is a non-zero constant, then we can view it as a polynomial in xn, and thus the resulting quotient is gonna be integral over this polynomial ring in n-1 variable. Alright, so let's use this as a motivating idea, and let's see how we could link this polynomial ring with a polynomial ring in n-1 variable. Now, our first observation is that this prime ideal must be principal and actually generated by some irreducible polynomial f. So why is that? Well, let's take any non-zero element in this prime ideal. There must exist a non-zero element because this ideal is not equal to 0. And then let us factor this element into a product of irreducible. We should be able to do that because this polynomial ring is a unique factorization domain. Now, by property of prime ideals, since this product lies in P1, one of these factors must lie in P1. And thus the ideal generated by that factor must also lie in P1. Since this ideal is prime, they must therefore be equal. Otherwise, we could have included this ideal into this chain and thus extending the chain, contradicting the assumption that this is a maximal chain. Thus, P1 should be generated by some irreducible polynomial f. By performing a change of variable, if necessary, without loss of generality, we can assume that f is a monic polynomial in xn with coefficients in the polynomial ring in n-1 variable x1 to xn-1. In particular, if we quotient the polynomial ring in n variables by f, we get an integral extension of the polynomial ring in n-1 variable. Thus now we see how to use the induction hypothesis. First, we quotient out every prime ideal in this chain by the ideal generated by f, i.e. by P1. Then P1 becomes 0, and distinct prime ideals remain distinct prime ideals by the bijective correspondence between prime ideals of this quotient and prime ideals containing P1. And next, we contract all of the prime ideals in this chain to the ring of polynomials in n-1 variable. Now, distinct primes must contract to distinct primes since this extension is integral. This is by the incomparability property that we mentioned. Now, this must be a maximal chain inside this polynomial ring in n-1 variable, because if we could extend it in any way, then that lifts to another term in this chain. So by induction hypothesis, we know that this chain here must have length n-1, and since the original chain just have one more term than this, it has the term P1, the original chain must have length nth. And thus we have shown that the polynomial ring in n variable is catenary, and all of its maximal chain of prime ideals have the same length n. In the next video, we're gonna prove the incomparability property that we have used in this proof.